Welcome back, everyone. I am absolutely thrilled to have you here for today's explainer because we are embarking on a really fascinating evolutionary journey into application architecture. If you've ever found yourself wondering how the software we rely on every single day is actually structured beneath the surface, well, you're in exactly the right place. We're going to break down how systems grew from these simple, isolated desktop programs into massive, distributed enterprise applications, and we're going to do it step by step.
But before we even get to that massive scale, consider this question for a second. How does a simple, basic HTTP request navigate the immense and, let's face it, often chaotic complexity of modern high-load enterprise systems? When you click Submit Payment on a massive global e-commerce site, what is literally happening behind the scenes to make sure that request isn't lost, your financial data is retrieved securely, and the whole system doesn't just instantly collapse under the weight of thousands of other users doing the exact same thing at the exact same time?
Okay, let's dive into this. Here's our roadmap for today. First, we'll hit the client-server foundation, then enter three-tier architecture, and see how that scales right up to n-tier layering. From there, we'll unpack layer responsibilities and rules, look at the trade-offs in enterprise apps, and wrap up with a look ahead at requirements engineering. All right, Section 1, the client-server foundation, setting our baseline with HTTP.
To really understand architecture, we've got to ground ourselves in the absolute bedrock. And according to the HTTP RFC 9110 specification, the relationship between our fundamental players is actually elegantly simple. An HTTP client is just a program that establishes a connection to a server to send one or more requests. On the flip side, an HTTP server is the program that accepts those connections, listens to the requests, parses them, interprets the semantics, and shoots back a response. It's a pure request and response dynamic. The client asks, the server answers. This dynamic is the foundational building block for literally everything we're going to discuss today.
Now, historically, how we've partitioned that client and server relationship has drastically changed. Think back to early computing, which relied heavily on a desktop plus database server model. Then, as the web evolved, we shifted into a browser plus web server split. And finally, as business logic just became way too heavy for a simple web server to handle, the late 1990s ushered in the era of dedicated application servers, driven by massive technologies like Java and .NET.
What's truly fascinating here is the contrast in where the application's thinking actually happens. In that early desktop era, developers built what we call thick clients. They were writing rich, computationally intense applications directly for user interfaces, like Windows. The core logic lived right there on your physical desk, and it just reached out to a standalone database server when it needed data. But when the web arrived, we flipped to a thin client model. The browser became incredibly lightweight, just handling the UI, and relied almost entirely on a remote web server to do all the heavy lifting. This shift allowed apps to be distributed widely, and it completely rewired the architectural landscape.
Which brings us to Section 2. Enter three-tier architecture, adding an application layer.
So as businesses moved online, simply having a browser talk to a web server, which then talked to a database, well, it just wasn't cutting it anymore. During the late 90s, three-tier architecture became all the rage because it provided vital layers of separation. You had a robust database tier running on an industrial-strength server. Sitting in the middle was this brand-new application tier managed by an app server. This is where your complex business logic lived. For example, in an early online banking app, this middle tier is what checked your balance before allowing a transfer, keeping that logic completely separate from the database and the user's screen. Finally, you had the front-end presentation tier, increasingly coded in HTML and JavaScript. And to make all these physically separate tiers talk to each other over a network, developers use these really complex distributed protocols like Corba and DCOM. Actually, here is a wild historical quirk about the three-tier era. It was so incredibly dominant that the designers of the Java programming language assumed three-tier would just be the standard forever. Because moving objects over a network between these separated tiers was so clunky in older languages, Java's creators baked a feature called serialization directly into the core language. Now today, that strict three-tier style has largely faded away, but that leftover serialization feature is still in Java. It's an absolute headache for modern language designers who have to maintain backward compatibility for a feature almost no one uses anymore.
Let's move to Section 3 and see how this builds. Scaling to n-tier architecture, the de facto standard layered monolith.
In a standard n-tier architecture, the components are organized into logical horizontal layers right within the software itself. You'll typically see 4 standard layers: the presentation layer for the UI, the business layer for rules and calculations, the persistence layer for database routing, like SQL, and then the actual database layer itself.
It's absolutely crucial to note that this is a technical partitioning. The architecture is grouped by technical roles, meaning a single business domain, say processing an e-commerce shopping cart, is actually smeared vertically straight down across all of those horizontal layers.
Now physically, these logical layers can be deployed in a few common topology variants. You might deploy the presentation, business, and persistence layers all as one giant block that connects to an external database. Or you could separate the presentation layer onto its own dedicated server, keeping the business and persistence layers together. For smaller internal company apps, you might even bundle the whole shebang, all 4 layers, including the database, into a single deployment unit. The key takeaway, the logical structure remains N-tier, completely regardless of the physical servers hosting it.
Section 4. Layer responsibilities and rules, maintaining separation of concerns and layers of isolation.
The real superpower of N-tier lies in its strict boundaries. The presentation layer doesn't know how to get customer data, it only knows how to format it for the screen. The business layer doesn't care about the screen at all, it just calculates values. And the persistence layer just handles the SQL. Interestingly, this perfectly mirrors Conway's law, which basically states that systems reflect the communication structures of the organizations that build them. It's a natural fit because companies already have dedicated teams of UI developers, back-end logic developers, and database administrators.
To enforce these responsibilities, we use the concept of layers of isolation. This dictates whether a layer is closed or open. In a closed layer architecture, a request moving top-down simply cannot skip a layer. A presentation request must go through the business layer to get to the persistence layer. This intense isolation means changes in one layer don't ripple out and break everything else. An open layer, on the other hand, allows a request to bypass it, which provides incredible flexibility, but obviously at the cost of tighter coupling. And this brilliantly illustrates how we can combine those concepts. We can safely add an open shared services layer, say for basic logging or simple date formatting, that the presentation layer needs to access. If we stuff it inside the business layer, we clutter our core business logic. Instead, we just add a new services layer below the business layer and explicitly mark it as open. This allows the business layer to use it, but it also safely permits the presentation layer to completely bypass the business layer and hit the services layer directly, all without breaking the strict closed contracts of our core architecture. However, we have to be careful because strict layered rules can lead to a really dangerous anti-pattern known as the architecture sinkhole. Imagine a super simple request to fetch a static company tax ID. The presentation layer asks the business layer applies 0 logic, it just passes it to the persistence layer grabs it from the database, and the data is passed all the way back up the stack with no processing whatsoever. Guys, this is a massive waste. It forces unnecessary object instantiation and processing, eating up memory and significantly degrading performance for what is literally just a simple pass-through request. Section 5. Trade-offs in enterprise apps. The hidden cost of simplicity.
When we evaluate the layered architecture style on a scorecard, it earns an excellent 5 stars for overall cost and simplicity. It's super familiar, natural to build, and cheap to maintain in its early stages. But look down at the bottom. It scores a dismal 1 star for deployability, scalability, elasticity, and fault tolerance. Because it is a monolithic deployment, meaning everything is bundled into one giant unit, you can't easily scale just one piece of it. If your business layer is under crushing load during a massive sales event, you have to replicate the entire application, database connections and all.
And honestly, that lack of fault tolerance is arguably its biggest vulnerability in a real-world enterprise setting. Because everything runs in a single process, one single out-of-memory error, maybe caused by a poorly written query in the persistence layer, doesn't just break the database connection. No, it crashes the entire monolithic application. Every single user is suddenly disconnected. And worse, the mean time to recovery is incredibly high. Restarting a massive enterprise monolith can take anywhere from 2 to 15 minutes. In a high-demand environment, a 15-minute outage caused by a single bug, that's a catastrophic failure.
Finally, Section 6. Next up, requirements engineering, moving from the structural how to the functional what.
So the crucial point to take away today is this. We've learned that architecture, like the N-tier model, dictates exactly how a system survives under load, how it scales, and ultimately how it fails. We've seen how logical layers beautifully solve the separation of technical concerns and map right to our organizational teams. We have successfully designed a robust, resilient physical and logical container. But the architecture itself doesn't tell us a single thing about what the business actually needs the software to do.
Which leaves us with one massive, lingering question. We know how to build the structure, but how do we know exactly what features to put inside it? How do we translate vague business desires into concrete instructions for those UI, backend, and database developers? That bridge between business need and technical execution is exactly what we will uncover in our next explainer on requirements engineering. Thank you so much for joining me on this exploration of application architecture.